think we can start and then let people join slowly. So good afternoon. Good afternoon, everyone. This is good morning for me, and maybe noon time for Livia, I believe. So today we have Professor Livia Lodhova from RWTH Aachen University, Germany, and she kindly agreed to give a colloquium for us on geoneutrinos, a new tool to study the Earth. So she's an active member of the Borexino experiment and Juno experiment. And let me just say a few words about her. So, we sometimes struggle to do one PhD, but she did two PhD. That is interesting. So she did an MA in geology from Comenius University, where my student Amina is a postdoc there. And then she did a PhD in geology in 1998 from the same university. Then she did a MA in physics in 2001 from the same place. And then in 2005, PhD in experimental physics. So we are talking to a person who did two PhDs in two different topics. Great. So I just want to say that, Livia always supported Indian students. So like in her group, she has a mini India. Lots of students and postdocs are working from India. And this is really, I must say that, very nice that you give the opportunity to our students to work on these cutting edge experiments and fulfill their dreams. We just hope that someday we will have our own high energy physics experiment in our country. But thanks, Livia, for your support, and keep doing that for our students. So I request you that, please take us to the world of geoneutrinos and let's see. Okay, Livia. So the floor is open for you.
Thank you very much, Sanjeev. So both for invitation and this wonderful introduction. And I'm really happy to have Indian students. They are really among the best students, and I'm absolutely happy to have them, and I hope to continue our collaboration. So let's start with the topic of today. So I will speak about geoneutrinos, and welcome to this journey to the center of the Earth, as it was in the famous book from Jules Verne. And at the end of this seminar, you can try to answer the question why this title, The Journey to the Center of the Earth, is actually a little bit wrong. Why we cannot go with geoneutrinos exactly to the core. So I will, of course, start with the definition of geoneutrinos. We need some terminology about the Earth. I will explain for those who are maybe not focused on neutrino physics, some very basic aspects which are important for understanding the measurements I will present. And I will focus on the Borexino geoneutrino measurement, the latest results, very brief introduction, comparison to the KamLAND results on geoneutrinos, and some outlook of this new field. So there are many processes that in millennia people observed on the surface of the Earth that demonstrate the power that is hidden inside the Earth. It can be a terrible earthquake, as on the top left you can see the photography from the terrible 2009 earthquake in the area of the Borexino experiment. Or it can be sometimes also dangerous, sometimes spectacular volcanic explosions, or it can be a demonstration of the old ocean sediments being brought to the surface of the Earth at this photography from the Grand Canyon. So one can ask, from where is coming the energy driving these processes? And today we will discuss how can neutrino physics help us to understand, at least in some way, from where the energy is coming, which drives these processes. So for this, let's define geoneutrinos. Geoneutrinos are antineutrinos from the decays of long-lived radioactive isotopes naturally present in the Earth. By long-lived, we mean the lifetime is similar to the lifetime of the Earth. So it means that from the point of the creation of the Earth, they just did not decay and they are still present. The dominant isotopes is the chain of uranium-238, thorium-232, and decay, not the chain, just single decay of potassium-40. As you can see, the number of antineutrinos, which we call geoneutrinos, shown in red, and the amount of the energy, which is then turned to heat, and we call this heat radiogenic heat, is perfectly well defined. So it means that in principle, if you measure how many neutrinos were emitted, you can directly know without any doubt how much radiogenic heat was released by knowing the energy balance of these interactions. Of course, in practice, it's more complicated because the flux which you measure on the Earth depends also on the spatial distribution of these isotopes. But this is the principle of the method to detect geoneutrinos to extract this radiogenic heat. The Earth shines in geoneutrinos with the flux about 1 million of geoneutrinos passing your thumb, so 1 centimeter square per second. This is a huge number, but comparing, for example, to the solar neutrinos, which are not antineutrinos, but neutrinos, it's about 4 orders of magnitude less. So let's start with some information about the Earth. The Earth was created by the accretion of small irregular objects, which as this proto-Earth was growing, the central part was heating, and it was forced the metallic core to segregate from the silicate from the silicate part of the material. This originally due to the very large heat produced as the binding energy of this small object, so which was heating plus a lot of radioactive material, the silicon part was melted, and we call it magma sea or primitive mantle. Please pay attention to this term of primitive mantle, because today geochemical models are describing the average composition of exactly this primitive mantle. Only later on, primitive mantle differentiated to the current mantle and the crust. So to the question, what is inside of the Earth, we can answer by different ways, depending what we study. We can study compositional layers, we can study mechanical layers, or some dynamical processes. I will now try to go a very brief, just basic definition of the terms from all of these points of view. So in the innermost part of the Earth is the metallic core, which is solid because of the pressure of the overburden material. It's iron and nickel alloy. Above this is a large area of more than 2,000 kilometer thickness, which is also metal, but it's not solid, but it's liquid. And there is ongoing convection of this metal, which in the middle of the magnetic field from the sun is somehow triggering and causing the creation of the Earth's magnetic field, so the so-called geodynamo process. So it's a very important layer for our life. Now, there is some kind of indication that this iron nickel alloy in the outer core has some admixture of at the order of 10% some lighter elements. As Sanjeev knows very well, this is the target of the study of the neutrino tomography of the Earth, and it's not the target of study of geoneutrinos, just to avoid some misunderstandings here. The overburden layers above the metallic core are silicate material. So practically, let's call it rocks. The division between metallic core and the silicate part is so-called D double prime layer. It's a very sharp seismic discontinuity. It's about 200 kilometers thick and not very well understood. Then we have the large area also of about 2,000 kilometers of the lower mantle, which is not molten. It's not liquid. It's solid, but viscose and plastic on the long time scale. So there is ongoing the mantle convection, as we can see on this simulation in the lower part. From this lower mantle, we don't have the samples. So we don't know very much about the composition of this lower mantle apart the modeling. Then on the top, we have more structurized layers. There is the so-called transition zone, this light green, which is also the seismic discontinuity, and where is ongoing the partial melting on the rocks to produce mid-ocean rich basalts, which are creating the oceanic crust. Then we have upper mantle, the dark green, which is chemically probably similar as the other parts of the mantle, but is different mechanically. It has two mechanical layers. It's more rigid part, which is together with the crust, creating lithosphere, and it's floating on the more plastic astenosphere. Then we have two types of the crust. As I was mentioning, the mid-ocean rich basalts, it's the material creating the oceanic crust, and it's melted out from the transition zone in the mantle. There is the extension process of this freshly created oceanic crust, which is then going under the other crust. It can be continental or oceanic in the subduction zones. Now, the oceanic crust is the most ancient part of the upper layer of the Earth and more complex in the composition. And it's there where most of the geoneutrinos are produced. Now let's discuss how we gain information about the inner Earth. So one tool is the seismology, which measures the propagation of the S and P waves produced in the earthquakes around the planet. The result of such seismological studies is the creation of the profile of the velocities of the P and S waves and of density profile, and of density. You can see the large discontinuity of this at the core mantle boundary, or at the inner and outer core, or at the upper layers, which is even more complicated. The important point is that seismology, even if it can provide information about density, does not provide any direct information about the chemical composition. This is the subject of study for geochemistry. We have, of course, direct rock samples, but they are limited in the depths from which they come. The deepest borehole created by people, it's 12 kilometers in Kola Peninsula in Russia. So you can imagine that comparing to the radius of the Earth, it's a very small number in spite of the big technological challenge. We have various tectonic or volcanic processes bringing even deeper material to the surface, but they can be often altered. And but nevertheless, we have no direct rock samples from the really lower mantle. For that, we rely on geochemical modeling. So as I have mentioned, this primitive mantle after the segregation of the metallic core at the ancient Earth, this is the topic to model its composition of this bulk silicate Earth of the primitive mantle for geochemical models. These models are exploiting this kind of observation. If you compare the abundance of various isotopes relative to silicon observed in the solar photosphere and in the carbonaceous chondrites, you can see this perfect correlation. So if you say that these trends are observed both in the sun and in the chondrites, then it is reasonable to assume that even the material from which the Earth was created had a similar isotopic composition. And then exactly this is what the geochemists assume. Then you have kind of, I would call it, boundary conditions of the composition of the mid-ocean ridge basalts, because they are melted out from the present mantle and so on. So here, an important concept for the geoneutrinos is that the sum of the abundances predicted by the model is kind of sum of the abundances in the lithosphere and in the mantle as of today. While in the lithosphere, from where we have the direct samples, we can relatively precisely estimate this the amount of radiogenic of the uranium and thorium and potassium, and that means of the amount of radiogenic heat, 7 to 9 terawatt. What is in the mantle, we can just estimate by subtracting this well-known part in the lithosphere from the modeling. And this is a big interval, from 1 to 27 terawatts, because as you can imagine, there are many systematic effects. So there is not just the one bulk silicators model, but many of them. Let's now speak about where uranium and thorium exactly are. And for this, we need a little bit to understand their chemical properties. So on this plot, we have the condensation temperature in the Earth, and according to this, the categorization of elements as refractory, so as those which remain in the Earth, and volatiles, those which stayed for a long time gaseous state and had higher chance to escape from the primordial Earth. And this is the normalization of these elements with respect to the chondritic meteorites. So you can see that uranium and thorium, those producing geoneutrinos that we can detect, are estimated to have at the same amount as in the chondrites. While potassium, that present-day technology is not able to detect, is a little bit in between refractory and volatile, and it's a little bit depleted with respect to the chondrites, according to the models. For the current geoneutrino analysis, often the analysis is done by fixing the ratio of uranium and thorium, which is kind of justified by these models. But of course, we want to test this with geoneutrinos. If the Earth, in the Earth, the bulk ratios of these elements is such as we assume based on these geochemical models. Another important characteristics of uranium and thorium is the so-called that they are lithophile, which means they are rock-loving. Because of this chemical compatibility with more rocks, this means silicates and not the metal, they are not expected to be present in the large volume of the metallic core. And as you are heating rocks, there is always a transition from the solid to liquid phase. And firstly, a lighter with the lower density material is melted out from the heavier residue. And what is important to understand that uranium and thorium are always bound more to the lighter liquid part. Just because of the gravity, this lighter liquid is going to the higher levels. So over the ages, the uranium and thorium is accumulating in the higher levels of the Earth, and mostly in the continental crust, which has the most complex history. So you can see if you go from the top to the lower layer of the Earth, we expect uranium and thorium to decrease from upper crust to lower crust. In the oceanic crust, which is much less complex in history and directly melted out from the depleted mantle, we expect less uranium and thorium and orders of magnitude less in the upper mantle. But that's exactly the question, how much it is in the upper mantle. This is just assuming one BEC model. Now we should tell a little bit about the Earth heat flow. There are thousands, at the order of, I think, 30,000 drill holes, mostly in the search for oil, along which the temperature gradient was measured. And by doing the modeling, you can also imagine how much systematic errors or effects is to be considered. you can assign a heat flow to construct the heat flow map of the Earth. When you then integrate this, there is geophysicists kind of agree currently on this number that integrally through the Earth is going out about 47 plus minus 2 terawatt of the heat or of the power. Now, what are the main contribution to this? One part shown on this pie diagram in green is the cooling of the Earth. So it's from the part of the accretion, the binding energy of this object, which did not left the Earth yet, and it's still the Earth is still cooling down. How much of this heat is there, we also don't know, and geoneutrinos there cannot really help yet. I mean, cannot help. However, roughly half, that's the general estimate, but we don't know also this, a big part is expected to come from the radiogenic heat. And that is where geoneutrinos can help, particularly to pinpoint the radiogenic heat from the mantle. So let's summarize. Geoneutrinos are antineutrinos emitted from uranium and thorium chain and from potassium, which are via nuclear physics bound to radiogenic heat. What is the main goal of the geoneutrino studies? But in order to predict the geoneutrino flux at a location of the experiment, and also to interpret the measurement in the terms of radiogenic heat, you need to know about distribution of the radioactive elements. And therefore, you need some discussion with geologists. So neutrino geoscience, as we often now call this field, it's a truly interdisciplinary field. So what is the expected signal of geoneutrinos? We often express it in the so-called terrestrial neutrino unit, which means one detected geoneutrino, one event, for 10 to the 32 target protons, because as I will tell you later, we detect geoneutrinos on the hydrogen nuclei, so on free protons, which means about 1 kiloton of the standard liquid scintillator detector per 1 year for a detector with 100% detection efficiency. Now, this is the map of the expected signal in TNAU coming from the crust. You can see that from the oceans, we expect very little, 5, something like this, geoneutrinos per year in 1 kiloton detector with 100% efficiency. We can see much more flux is expecting from the continental crust, the green areas. And in the region of Himalayas, when the crust is almost doubled due to the orogeny that created Himalayas, we expect about 50. The situation in the mantle is even more complicated. We expect up to maybe 10 TNAU, even by exploiting the model or hypothesis that the so-called large shear velocity provinces observed by seismologists corresponds also to geochemical inhomogeneities, and that the uranium and thorium is concentrated there where are these provinces of velocity anomalies. So to observe mantle signal on top of the relatively known crustal signal is a really challenging task. Now, for those not specialized in neutrinos, let me say a few words to introduce them as a particles after I have a sip of water. So neutrinos are very special. They interact only via weak interactions, which means they are difficult to detect. We need large detectors. We need to go underground to shield against the cosmic radiation. And we need extreme radio purity of the material in order that the events are recognized with respect to the radioactive decay, which are very common actually in our bodies and in the material around. This difficulty to detect them, however, also means that the low probability to interact, that they bring unperturbed information about the source. It can be sun, or astrophysical object, or even the Earth, as in the case of geoneutrinos. Neutrinos are also very special that their mass is orders of magnitude lower than the mass of other elementary particles, and we actually don't know why. There are many other open questions in neutrino physics, but this does not mean that not knowing the all information about the properties of neutrinos, that it would hinder the usage of geoneutrinos to study the Earth. Nevertheless, we need to understand a little bit the process of neutrino mixing and oscillation. So by neutrino oscillation, we mean practically that, maybe I should tell that we have three kinds of neutrinos when it comes to the flavor eigenstate. So when it comes to the electron, muon, and tau flavor in the coupling with the charge lepton. So all geoneutrinos are created as electron flavor, typically in the beta decays along the uranium and thorium chains. Now, because the neutrino has non-zero rest mass, and the flavor eigenstates and mass eigenstates are not the same, and the mixing matrix which connects them has non-zero off-diagonal elements, this we call mixings, there is a probability which depends on the energy and baseline, so the distance between creation and detection of neutrino. The flavor composition of the flux is changing. So the probability at the detection point is different. So the probability to measure the original flavor can be altered. And you can measure also the flavors which were not present in the original flux. Now, this is important to remember because finally the interaction with which we measure geoneutrinos today is sensitive only to the original flavor, to electron flavor. So we will speak about the electron survival probability of geoneutrinos. There are many kinds of geoneutrinos around us that span from several orders of magnitude of energy. Geoneutrinos are of the MeV energy, the same energy range as solar neutrinos or reactor neutrinos. But today our focus is on the geoneutrinos. There are two experiments which succeeded to measure geoneutrinos so far. It is KamLAND in Japan and Borexino in Italy. Both experiments are practically big balls of liquid scintillator. KamLAND about 3 times bigger than Borexino, Borexino being about 300 tons, in which the scintillation light is observed by an array of photomultipliers. All this so-called inner detector is then surrounded by water, both in KamLAND and Borexino, which serves as a passive shield against the external background and also with an active veto to see the cosmic muons which pass the detector. The cosmic flux is in both cases shielded by the overburden mountain or rock because experiments are placed in the underground laboratories. And of course, both experiments had to fight the radio purity of the liquid scintillator and other construction materials. The two experiments are completely complementary because they are in different geological settings on other parts of the Earth. And the original, let's say, main purpose was very different. KamLAND was constructed to measure reactor antineutrinos with the same interaction as geoneutrinos. And therefore, originally, before the Fukushima disaster, the background from reactor neutrinos was very high. Borexino instead was constructed to measure solar neutrinos, which the measurement requires much higher radio purity, which was also achieved in 15 years of R&D of Borexino work. And there are no nuclear power plants in Italy. So originally also the background in Borexino from reactor neutrinos and non-antineutrino backgrounds was much lower. Here is the history of various observation or studies of geoneutrinos between KamLAND and Borexino. I am not, of course, going through all this history. What is important is that the current precision, which is the very recent KamLAND update from this year, reach 15 to 16% precision. And what I will focus on in this talk is the Borexino measurement from 2020, which reached very similar precision of 17 to 18%, with 6 times smaller statistics, mostly because of the lower systematic error. So let's speak now about Borexino collaboration. There are about 100 scientists from Italy, Germany, Russia, France, US, and Poland. The Borexino detector, I have already introduced the main features, is placed in the Laboratorio Nazionale del Gran Sasso, so the largest, what regards volume, underground lab in Italy. It operated from May 2007 until October last year. We actually were forced to stop, so our data set is complete. And the main feature of Borexino liquid scintillator detector is that it was the world's radio purest material detector ever achieved. It was critical for the solar neutrino studies, and Borexino really produced enormous amount of measurements regarding solar neutrinos, but it was, of course, an important advantage also for geoneutrinos. We observe about 500 photons per MeV, which brings us to the resolution of about 5% at 1 MeV, 10 centimeters position resolution, and we can also do some pulse shape in the identification between alphas and betas, the best. So here is the photo from the CCD camera mounted inside the detector. On the liquid scintillator, hold in this, you can see the thin nylon vessel balloon. Out of this is the buffer liquid, very similar in density, but does not scintillate. And you can see the PMTs with the whinstone cones to direct the optical focus towards the center of the detector. So now when neutrino or antineutrino interacts, it has to produce somehow charged particles. I will tell you how exactly. In case of geoneutrinos, and it is the charged particle that excites the molecules of the liquid scintillator, so the aromatic organic compound, and it produces isotropic scintillation light that we then detect, and from counting of the number of photons on PMTs, we get the estimate of the energy. By searching for barycenter of the detected light, we can find the position of the event, and we get the GPS time for each trigger. Of course, we had to somehow calibrate our detector, so we put many radioactive sources through the volume of the detector in order to understand how our reconstruction algorithms work. Like this, we could tune our Monte Carlo. So we have a Geant4-based tracking code. We track the light through the detector. We perform electronic simulation. And finally, we have the same software which is used to reconstruct the real data to reconstruct the Monte Carlo data. Here you can see the comparison of the measured calibration data, gamma peak of various energy, with respect to the Monte Carlo. So we have reached about 1% precision in the smaller fiducial volume used and the energy of solar neutrinos, and about 2% for larger volume and larger energies. So here is in the more detail the so-called inverse beta decay interaction used to detect geoneutrinos and reactor antineutrinos. This is the same. we are sensitive only to the electron flavor component of the incoming flux because it's a charge current interaction. And antineutrino interacts with proton, so the free hydrogen, free proton. What is produced is the positron, which deposits its kinetic part. The amount of this kinetic energy is proportional. It's directly related to the energy of the original antineutrino. So with the amount of energy, which is above the 1.8 MeV kinematic threshold of this interaction, there is some energy needed because the created neutron is heavier than proton. So the antineutrino has to have some original energy, at least 1.8 MeV, to enable this interaction. Now, after the kinetic energy of the positron is deposited, it's a very quick process. Then typically when the positron already deposited its energy, annihilates together with another electron from the material around and produce two annihilation gammas. So when antineutrino is at the threshold of 1.8 MeV energy, the visible energy of the prompt signal is 1 MeV of the annihilation. This process is very quick. So all this energy is measured as one prompt signal related to the energy of geoneutrino. So we are doing the spectral fit of the prompt signal related to the positron deposition. Together with positron is created also neutron, which first is thermalizing, and then it's captured on proton. And this deuterium is created in excited states, and in the de-excitation produces 2.2 MeV gamma. So the delayed signal, which we search for the time and space coincidence with the prompt signal, is always 2.2 MeV gamma, which we detect by the fact that gamma is doing many Compton scattering, and these many Compton electrons are finally produced very quickly, so we see them as one flash of light corresponding to 2.2 MeV gamma. How much geoneutrinos we expect in Borexino? In order to do such calculation, you have to know something about the distribution of the uranium and thorium in the Earth. So for the mantle, we can do some, we can consider various bulk silicate Earth models as I introduced them. For the crust, there are general models which say what is the average composition of the lower, middle, upper crust, and in some voxels of the 3D bins, let's say, of the crust, there are such databases which say how thick is the upper, lower, and the middle layer of the crust. You can do such averaging and approximation for the crust far away from your detector, but when you go closer to the detector, of course, you have to know more precisely the composition. We call it LOC, like local crust, which can contribute up to the 50% to the overall signal from the area of a few hundred kilometers. So you have to do a detailed geological study. If you then know how much uranium and thorium you have around the detector, if you know the energy spectra per decay of the mother element, and here we can see potassium 40, uranium 308, and thorium 232, and 1.8 MeV threshold of IBD, we can see that we can measure only the uranium and thorium tails with different endpoints, which helps us to disentangle the different contribution of uranium and thorium. If you know the energy-dependent cross-section of the IBD interaction that is known very precisely from the standard model, if you know the survival probability of the electron flavor, it's about 55%, you can calculate the expected spectral shape and the overall rate. And for Borexino, it's about 28 to 45 TNU. So a relatively standard number comparing to other local crustal, continental crust locations. Just to tell, there has been done a detailed geological study of the area around the Gran Sasso. It was not done by Borexino collaboration, but it was done by geologists and physicists from the Ferrara group. I have mentioned this effect of neutrino oscillation. Just let me remind important effect. So the so-called oscillation length, so this is the baseline over which one complete change of the flavor occurs. For 3 MeV antineutrino, which is the typical energy of geoneutrinos, is about 100 kilometers. This means that for geoneutrinos crossing the whole Earth, there are many oscillation cycles, and finally, it is rather safe for the precision of the current experiments to assume that we don't see the overall change of the spectral shape, but rather the suppression of the amplitude, and the survival probability is about, on average, is 55%. This approximation is not possible to do for reactor antineutrinos because reactors are strong sources at singularities, and in order to consider the background from reactor antineutrinos, you really have to do the sum over each reactor in the world. So finally, we select our IBD inverse beta decay candidates by searching for space and time coincidences. We have the energy, time, and position of various events. Like this, we have found 150, we have to tune of, I'm anticipating, we have to tune our selection cuts. I don't want to go to the detail, let me check also the time. I don't want to do the details, but I just want to tell that there is a lot of work regarding the tuning of the cuts, but practically you have to, understanding your detector, you have to search for the correct energy points and spatial positions of the events in order to optimize your sensitivity and signal to background ratio. Finally, we have found about 154 IBD candidates. Their distribution in the energy of the prompt candidate, of the delayed candidate, the distribution in time and spatial distribution is compatible with our Monte Carlo simulation. So there was nothing weird what we have observed. And in order to disentangle the contribution of geoneutrinos, reactor neutrinos, antineutrinos, and other backgrounds, you have to do the spectral fit of the prompt candidates. For that, you have to constrain the antineutrino background. I have already mentioned that we have some cosmogenic background. You can have accidental coincidences, so two completely uncorrelated events just falling within the coincidence cuts, or you can have some backgrounds due to the internal radioactivity. There are the special techniques that we developed so we can study with independent data sets, cosmogenic, so-called alpha N background and accidental backgrounds. And overall, by also very detailed study, we have found that our overall non-antineutrino background is about 8 events from these 154 overall IBD candidates. We have also studied neutrino background. Of course, we have done our estimation of the number of events from reactors by getting the information from the IAEA agency in Vienna, calculating the survival probability and knowing the monthly load factors, considering the systematic uncertainty in the shape of the reactors. And we also have studied the amount of the background from atmospheric neutrinos, which at this MeV energies has very large uncertainty. But finally, the amount of events expected from atmospheric is very small, so we kept it practically as a systematic error. So then we have done the fit. So we have taken the energy estimator, we call it charge of the prompt candidate. We have done unbinned likelihood fit. This is shown in binned just to show for the demonstration graphically. And we have done the following fit. We fit the geoneutrinos in which uranium and thorium signal is constrained to the chondritic ratio. I justified why we think it's reasonable. We have fitted a reactor spectrum. We kept it completely free. and the non-antineutrino background shown in these other colors, which are constrained based on the estimation from the independent datasets. The resulting parameters are the number of geoneutrino events and number of reactor events. So totally, we measured about 53 geoneutrinos with 17 to 18 precision. The number of sigma is more than 8, so there is no question we measured geoneutrinos. What validates our antineutrino detection is that our number of reactor antineutrinos is completely consistent with the expectations for which we have done our calculation. Then when we compare geoneutrino signal with respect to the different bisilicate Earth model, we are in perfect agreement. However, we prefer the models which predict higher amount of uranium and thorium in the primitive Earth. I have prepared here some comparison with KamLAND. This is the latest data set presented in 2002 paper, split in the 3 phases, shown the first one after liquid scintillator purification and after Fukushima disaster, when the amount of geoneutrinos shown in blue with respect to reactor and other backgrounds is the highest. This endpoint here corresponds to the endpoint in Borexino at the end of the blue point. So the energy scale, sorry, is not the same. That's how the things got published. But overall, you can see that Borexino detected about 53 geoneutrinos, KamLAND 183, with the very similar precision, KamLAND a little bit better. Both experiments try to do a fit in which uranium and thorium is not constrained to the chondritic ratio, but it's free. In Borexino, we performed a sensitivity study that we injected uranium and thorium chondritic ratio, but we got rather flat distribution with thorium often railing to 0. This is the result of such a fit in data. So practically, we concluded we have no sensitivity to measure uranium and thorium. KamLAND has a little bit more statistic, so they've got a better result, but still you can see the 2 sigma contour is crossing the 0 axis. So we still need for a firm information about the uranium and thorium and experiment with much higher statistics. Borexino also made a fit in which the lithospheric expected contribution based on the local geological study is constrained. And like that, the Borexino excluded the 0 mantle signal at 99% confidence level. Now, this is a bit tricky part. I don't go to the detail, but in order to convert the measured signal in the terrestrial neutrino unit to the radiogenic heat, one has to consider the possible distribution of uranium and thorium in the mantle. And like that, our interval in TNU was converted to about 25 plus minus 10 terawatt based on uranium and thorium only. To this, you have to add the radiogenic heat from potassium. There are some models estimation, plus the relatively known lithospheric heat. And we get about 38 terawatt to be compared to the overall flux, which was estimated from the measurement of the temperature gradients in the boreholes of 47. So Borexino experiment is seeing very limited contribution of the latent heat to the overall Earth's heat flux. This is the same plot to be compared to the preliminary KamLAND plot. The actual latest paper does not have this update. They are compatible apart the 2 sigma something difference, so it's not very highly significant, but there is a difference that Borexino is more compatible with the bulk silicate models predicting the highest uranium and thorium ratio, while KamLAND the lowest. This tension is there, of course, if you assume that the mantle under KamLAND and Borexino is the same. So let me summarize. Borexino provided a geoneutrino measurement, it's 2020, with the data up to April 2019, which reached the precision of 17 to 18%. And I think the big success together with the KamLAND is that this measurement is in general agreement of our geological predictions. However, we need future experiments to provide more statistics, maybe on multi-site experiments, on all the experiments at geologically particular locations. So Borexino stopped data taking, so we don't expect anything new. KamLAND just done a new update. SNO Plus is a liquid scintillator detector focused on double beta decay, but geoneutrinos will be measured. They just fill the detector, so hopefully news will come. On Juno, I have next slide. Jinping is a 5 kiloton detector suggested in the deepest lab in Himalaya region, but it's unclear how and when it will be constructed. But the geoneutrino detector would be the ocean bottom detector suggested in Hawaii. So 10 kiloton movable detector on the oceanic crust, which would directly, in principle, measure the mantle signal, so the main unknown. So this would be my favorite detector. However, let me comment on Juno, so the experiment on which I also work. This is the modeled spectrum of 1 year. So Juno is 20 kiloton detector in China under construction, in which we expect about 400 geoneutrinos per year, so which is about double than the statistics of both KamLAND and Borexino together. Neutrinos shown in orange or yellow. So there is a large background from reactors to geoneutrinos, but the statistics helps. And practically, Juno can reach in 1 year the precision of the current KamLAND and Borexino experiments, and after several years can also measure uranium and thorium separately. So yes, with this, I stop with this nice photo I took on the flight from Kathmandu to Bhutan of the Everest, which demonstrates the radiogenic heat in action. So thank you very much.
Thanks a lot, Livia, for this nice, your talk, your presentation on the journey of geoneutrinos through Borexino and KamLAND. And also you mentioned about the future possibilities. So now the floor is open for the question. So yes, there is a question from Professor Vivek Datar. So yes, sir.
Yeah, can you hear me, please?
Yes,
yep.
Yes, I can hear.
Okay, I have a couple of questions, but maybe I'll just start out with the first because maybe there'll be other questions that I can combine. The question relates to Juno, which is that if I remember, it's not at such a great depth. I think the depth is, or the overburden is like 500 meters or something. So how do they hope to tackle the cosmic ray background?
Yeah, so
or is it that they will only consider an inner core and use the rest of it as a veto?
No, it does not help like this. So you are right. It's it's about 650 meters. It's the top of the experimental hall, and the background will be much bigger, the cosmogenic background. Doing veto does not really help because the muons which pass through the rocks, they can cross the detector. So the big background, for example, is this green one, lithium helium. It's the background from the spallation of muon on carbon in the liquid scintillator, and they decay beta plus neutron, so they produce exactly IBD-like event. So it means we have to reconstruct the muon track through the detector, and at the order of 1 second to veto the area around the muon track. And we have already the algorithms for, based on simulation, of course, to do that. And we believe that we can have the like 10 to 15% loss of exposure by doing this. In Borexino, for example, we had in the latest update only 2% reduction, while in Juno it will be much more, 10 to 15%.
Can I ask another question, Sanjeev?
Yes, please.
Okay, the other question relates to potassium-40. I remember a long time ago, this was showcased as a big, something that was people would want to know, potassium-40, neutrinos. Now, of course, there are two decay modes. One is the electron capture and the other is a beta decay. The electron capture leads to a monoenergetic neutrino line. Do you think if an indium detector were ever built, that could address this potassium-40 electron capture?
Which detector? Sorry, can you?
Yeah.
Which detector you mentioned?
Oh, the indium detector of Raghavan.
Okay.
Because that detects neutrinos from the sun.
Yes, with the charge.
And,
yeah.
Of course, the branching ratio is only 10% from the potassium-40. But however, it's a line. And so if you could somehow manage the sensitivity, and of course the size, because the size is, but at least that is through the charge current interaction. So cross section is not.
Yes. So you mean to measure this neutrino, right?
Yeah.
From this branch. Yeah.
That was the lens experiment.
Yes.
It never got, I think, funded, and also it's not.
Exactly. So I know I was lucky enough. So Raju was in Borexino experiment. So I met him a few times when I started. But in principle, it should be possible. But I think the sensitivity to that, it's not that great. So, but I cannot elaborate more. I would have to make it up right now.
Okay, thank you.
Great. So there are other questions from
Sanjeev. Can I ask a question?
Yes,
actually,
please.
I'm asking some different. My main computer is not working, so I don't. Can you hear? Yeah, you can hear me, no? Okay.
Yes, clearly.
Okay, fine. All right. Now, actually, my question is about this matter effect for the neutrinos coming through the. I was just curious that the solid part of the matter. If the matter is in crystalline phase or in the liquid or amorphous phase, are the matter effects different? What I mean is that if it's a crystalline plane, then at some places neutrino will go straight through, will not meet much matter. And if it's amorphous or liquid, it will always meet some matter. So does one expect different kind of matter effects depending on crystalline phase or amorphous or liquid phases?
So what matters here, Sanjeev, correct me if I am wrong, is the electron density.
Right.
And if you, so in principle, if you have the same electron density in liquid or solid, I don't think it should change.
No, but that's on the average, if the neutrinos coming through and the crystalline planes which are aligned, then the neutrinos going in between crystalline planes wouldn't meet any electrons. Whereas the electrons, you see, there were the atoms which are directly on the path of the neutrinos. There'll be huge amount of electron density. That's what I was thinking.
But all the matter effects, the deviations from some averaging over the Earth is at the level of some percent. So comparing to the 20%, 15-20% precision of this of the current experiments, it's quite negligible. Okay. But for the future experiment, as you know, if you want to go to few percent, even the local matter effects, for example, from the area close to the detector, must be more carefully studied. Then it might start to be not possible to average, because if you have the oscillation length of 100 kilometers and you have nearby detector some rocks which are close to the detector with high solid angle, you need to consider for a precise measurement the matter effect and the real oscillation length, not just on the average.
Okay. One more question, Sanjeev. You mentioned about the outer core of the Earth and lower mantle boundary is about 200 kilometers.
Yes.
I believe this will be probably some kind of a mixed phase because this is a solid liquid boundary.
Yes.
So this radiogenic heat, which is being released, does it affect this thickness? Because the mixed phase is very sensitive to the heat available?
The thickness. So the radiogenic, I don't know. I think this is very, not very well understood, this transition zone. Okay. It's right between the metallic liquid and the solid mantle. I think that there is, right. Yeah, but I think from the point of view of the radiogenic heat, it's not that dominant, because volumetrically, unless there is some, there are, I think, even some ideas that it could be some, that in the subduction zone, sometimes they can reach down to the core, and you can have some enrichment at the very lower layer of the mantle of uranium and thorium. But as the thickness of the D double prime layer, if you assume just the standard, not some special effect, it should not have a big contribution to the radiogenic heat.
Okay, thank you. Thank you.
Actually, from seismology, if you're talking about the core mantle boundary, like where yes. the sudden jump in the density occurs, yes. the uncertainty is around 10 kilometers. This is the estimate from seismology. So this okay. D double prime layers is different than the core mantle boundary. So if you see the core mantle boundary along the radius of the Earth, we know that it happens from PREM profile of the Earth around 3480 kilometers. And we have an uncertainty of around 10 kilometers from seismology. Now, we posted a paper 2 days back where we showed that with neutrino oscillation, and if they feel matter effect, then you can also get an estimate that where the core mantle boundary lies. But that error is around 100 kilometers with the future neutrino experiment. So if we have more experiments, bigger neutrino experiments, maybe after 20 years down the line, you can get an estimate which is comparable to the seismic uncertainties. But anyway,
with atmospheric neutrinos, not with
with atmospheric neutrinos, definitely, because the geoneutrino stuff is happening around the crust, basically, right? Most of the activity.
From the mantle also. So the question right. exactly is how much is from the mantle. So because of the chemical properties of uranium and thorium, they are concentrated in the crust. But there is some mantle. We don't have a reason to assume there is no uranium and thorium in the mantle. In the process of differentiation, a lot of uranium and thorium was taken from the mantle, let's say it easy way, to the crust. But there is something, but we don't know how much. So I think geologists, they have no doubt there is some uranium and thorium.
With atmospheric neutrinos, the neutrinos should need to cross the core mantle boundary. So that neutrinos has to be like core passing, like, if they are passing through mantle, then core and then mantle, then basically they feel the matter effect. And the matter effect is like a coherent, property, like, there is a coherent forward scattering is happening and you see the matter effect at the end. So, in your oscillation, when you estimate the oscillation probability, that can be altered depending on where you assume your core mantle boundary. So you really need long trajectories of atmospheric neutrinos passing through the core. This is the nutshell, like if you want to be sensitive to the core mantle boundary location using atmospheric neutrinos. But I think geoneutrinos will not be able to say much about CMB location, the core mantle boundary location.
No, absolutely not.
Yeah.
I mean, we don't measure the directionality also, right. to the contrary of atmospheric. So we measure kind of integral flux of what comes to the detector.
Right. You need directionality, which is possible like in water detectors or like liquid argon detectors.
Yeah,
or
but
like,
a
detector
the current,
like
I mean, it's very difficult because, it's in liquid scintillators, probably impossible.
Right. I can see a hand by Professor Datar. So yes, Professor Datar.
Yeah, I just wanted to ask you, what is your comment on a possible detector near the Himalayas? We are thinking of now a site in the Himalayan region. That is where the
also in
Indian
India,
subcontinent goes under. Pardon?
You mean the Jinping, or you mean Indian?
No, not Jinping. This is in India.
India,
We are thinking of a lab because we have stuck with the Tamil Nadu lab, so thinking of moving out. And so the Himalayan region is very attractive from the point of view of large overburdens, because there are high mountains in Himalaya.
I mean,
also the infrastructure is growing and whatnot.
I think to be honest, for mantle geoneutrinos, I don't believe it's useful. This is also my opinion for Jinping, because I mean, you need to model extremely thick and complicated crust there, and I think it's almost impossible.
But from the point of view of being a hotspot, is it a good idea?
Well, it's a hotspot in a way that the signal is very high. You are far away from reactors, so you can get the background from reactors very small, and you can probably go deep, because even if you go horizontally, you have thousands of meters above. So you can get probably very good shielding. So you probably can get backgroundless measurement. So you can so it could be even interesting for the measurement, like checking maybe the crustal composition there. But I think it's very, very difficult to, under the strong crustal signal, to measure the mantle. So for the mantle, I think it's very difficult. For checking the models of this complicated crust, it could be useful.
Okay.
So I just want to add, Livia, the question that Professor Ajit Srivastava asked about the matter effect. And so I just want to add that, in neutrino oscillation, when we have this Wolfenstein matter effect inside the Earth, you basically rely on the charge current interaction of neutrinos with ambient electrons. So what matters is the radial distribution of electrons that neutrinos will face along their trajectory. Now, if the composition of the Earth is different, then that can also affect the number of electrons, right? Because, if we assume that the Earth is neutral, and if it is, say, isoscalar, which is an assumption, then your number of electron, proton, and neutrons are same, right? But what matter effect can tell you is how much electron I have faced on my way. And if suppose there are some big water cavities or some different structure, then what would happen? The number of electrons that the neutrinos will face may change, right? So it is a question of, again, amount of electron will be different. And you may discover a big water cavity. Suppose in a neutrino trajectory, if there is a big water cavity, it has to be really big, because the effect has to finally sustain. When the neutrinos reach at the detector, you need to see some deviation from your expectation.
But it would be very hard with geoneutrinos, because we measure the integral flux. So from the number of geoneutrinos, we have to assume some density to get the abundance and then the radiogenic heat.
No, my comment was with atmospheric neutrinos. Definitely, this is possible.
Yes.
And also in MEV energies, your matter effect is also small. Like you really explore Earth's matter effect when you have GeV neutrinos passing through baseline of 5,000 kilometers, because the θ13 mixing angle gets amplified inside the matter, which is called the resonance matter effect. So we don't see that resonance with solar or geoneutrinos. That is possible with atmospheric neutrinos, and you need a baseline of above 5,000 kilometers. So I just thought that, because Professor Ajit Srivastava raised this question. So are there any other questions or comments from students or whoever is attending this talk? Like Anil, you have any comment? You want to make some comment?
I have a question, but before that, I can make a comment on Professor Ajit's question. So what he is asking is about, if let's say the Earth, some layer in the Earth is a crystalline. So since crystalline structures are arranged in a particular way, so there is a possibility that when a neutrino is passing through those structure, it doesn't encounter any electron and any atom. Like it is a kind of channeling effect. And in around 2006, there was some popular article, or an article roughly with less technical detail. What they were telling about is the diffraction pattern in the neutrino when it passes through the crystalline Earth. And then what the conclusion was that the technologically this diffraction tomography of Earth is not feasible. So I think this article was in the same line what Professor Ajit is.
Okay, thank you. That's exactly what I had in mind.
Yes, great. Thanks.
Okay, thank you for thank you for
yeah. So it is a kind of channeling effect. It is just like the X-ray diffraction.
Exactly. Channeling effect. Yeah, that's what I was thinking.
No diffraction. But what they concluded is that it is technologically not feasible.
Okay.
Yeah.
Thank you.
Thanks,
But
Anil.
again,
Yeah,
atmospheric neutrinos, right? It's not
Yes.
geoneutrinos. Okay.
Probably not through geoneutrinos. Yes, probably through atmospheric neutrinos. Yes. Yes.
Great,
Yes.
Anil. Yeah, we mentioned a sentence in our paper, but yeah, it went out of my head. But great. Yeah, there was a paper. There was a paper, and they concluded that technologically it may not be feasible. Yeah.
Yes. And now,
what kind of theory? If this crystalline errors, I don't know this.
yeah, I think that article was not in that detail if I read, but it was mostly like you need too many detectors at many locations, and because of that, currently technologically it is not feasible.
No, but the model of the Earth, it's very non-standard model somehow.
Yeah,
right?
yeah, because it's mostly amorphous, not that like, for example, even the outer core is liquid. The mantle is also a kind of plastic. So having a crystalline Earth, maybe in the core crust, you can find some areas which are crystalline, but like mostly it's amorphous, I think.
Yeah.
So coming back to my questions, I have like one question is that like we have in the core, we have some heat which is kind of dissipating. So this heat from the radiogenic component, how much is it compared to that the heat already there in the core?
So we still don't know precisely because it depends. So for example, here this plot. So if you can see this is the decompose. So on here we have the total heat in terawatts, and this line horizontal is this 47 plus minus 2, which is the upper limit. Let's say what is going out of the Earth.
Okay.
So in this color, it's the amount of the radiogenic heat from uranium, thorium, and potassium from the lithosphere, which is the same for all models. These different bars are for different bulk silicate Earth models. They differ in the contribution of the mantle radiogenic heat, orange, because different BSC models predict different uranium and thorium in the primitive Earth, so after subtraction of the same lithosphere in the mantle. And the blue one is the amount of the latent heat, so it's the sum of cooling the core and mantle. So you see, I mean, what is radiogenic heat predicted by the BSC model to reach the total upper limit of 47 is the space of the latent heat. So you see, it can be the majority for Javois BSC models. It can be half for some of them. If you take Borexino experiment, this is the dot of the measurement, it leaves very little latent heat from this kind of original cooling of the Earth.
Okay, so in Borexino experiment,
we don't know yet. I mean, the precision of the measurements, it's too big.
So in Borexino experiment, is there a way to know that the particular neutrino is coming from mantle or is it coming from core?
No.
Okay. Yeah, because I'm wondering like why there is no radiogenic component in the core. I mean, because uranium, thorium, they are the heavy metals. Why are
they don't like the elements are not structured based on their average density. They are bound. Uranium and thorium are trace elements which are bound to the crystalline structure of other minerals, and they are these lithophile characteristics. So they bound to the silicates, not to the metals. So we don't really expect them in the core.
So it's like overall density of the molecule is a bit lower, so that's why it goes towards the rock.
It's more with the radius of their ions, how they are compatible with the crystalline structure of the minerals in the mantle. Also in the mantle there are crystals. I mean, there is a minerals there have their crystalline structure, and how they are like the substitute elements of the major rock forming minerals in the rocks of the mantle of the peridotite.
Okay, okay. So it's like that most of these minerals, they are found in the crust and maybe a little bit in the mantle.
Exactly. So if you heat the rock, because they don't form the main crystallic structure, they just substitute the other elements, and then if you heat, they are easy to leave, let's say, and they go to the melted out liquid lighter part, and because it's really like it's the lighter magma that the solid residual, they go up and accumulate in the differentiated part, typically continental crust.
Okay, okay. So it's like
the standard geological picture. Let's say that there have been also some suggestion of some uranium in the core. I think it was Herndon who was suggesting like really a fission occurring in the core. But even with geoneutrinos, like they would produce some more reactor-like spectrum. I think I have even a backup slide here. It's called a georeactor. So you could have, like, there are some suggestions of uranium deposits producing fission, really, somewhere in the core. But if you constrain they would have similar spectrum as reactor antineutrinos. And the oscillations would be so far away from the detector, would be very fast. So you see just some average spectra, independent of the distance from the experiment. But finally, we placed very strong limits. If we constrain the reactor spectra that we can calculate with some % precision, we don't see such. It's really what is suggested is practically excluded by both KamLAND and Borexino.
Okay. Thanks.
Sanjeev, can I ask a question?
Yes.
Yeah, just okay. Very hypothetical question. I mean, the one very big question, of course, is what is the inner composition of moon? So, so is there any possibility of putting up a proposal for setting up a neutrino detector on moon? Because then you will know what is in the core of the moon.
I have no clue. But I think first we should put it all under the ocean, which also nobody wants to pay.
Okay. All right.
Actually, I think, Livia, 2 months back, maybe Anil, you can correct me, there was a paper where people were, talking about some detector to see some signal from moon, right?
Really?
Space detector or something,
I see. Yeah,
There was a paper. There was a
There
paper
was
by US group.
There was one paper 1 month back regarding the dark matter. What they want to put some detector on some asteroid or something, so they can measure the flux of the dark matter as it orbits the sun and goes away and close to the sun. And there was one paper where the shadow of the moon can be seen in terms of neutrino or something. Yeah, so somewhat like this.
Super K. That Super K has seen the shadow of moon. Yeah, Super K has seen.
I don't see any detector exactly on the moon, but maybe some detector in the space. That kind of people talk about detector in space.
I mean.
Yeah, I was thinking more like detecting neutrinos from the moon. So then only you know what's inside the moon, at the core of the moon.
Exactly, but I think I really cannot imagine. I mean, we don't know how to detect with a small detector geoneutrinos from the Earth being on Earth.
Yeah.
So to detect something in the space or bringing it to the moon small, the big we cannot bring, and the small we don't have the technology.
Right. Yeah, sure. Just for a fun question, okay?
Yeah.
Okay.
One should think big.
Right. Yes. That is really important. At least we should think. Our imagination should not be stopped.
We should think big for a small detector.
Exactly. Yeah.
Right. And any other questions, comments from anybody? Like, you can ask any question to Professor Livia. If you have any curiosity or anything about Juno or Borexino, so you can ask.
Okay, maybe I can ask this question about Juno,
right.
Not related to geoneutrinos. How are you doing in terms of, the energy resolution that is required to see these small differences in the oscillation? Yeah, for the mass hierarchy.
So, I mean, the energy resolution is absolutely correct. What you say, that it's the key feature to have like, we need like 3% energy resolution at 1 MeV to resolve the fast oscillation wiggles of reactor antineutrinos.
Mm-hmm.
And so we believe that we can reach this by, I mean, the combination of like statistical effects. So we have to have very original light yield, very high, about 20,000 photons per MeV, very transparent scintillator, hard, like 78% geometrical coverage with PMTs, like 30% conversion probability from photon to photoelectron. And for the systematic effects, we need a very extensive and regular calibration campaign with many sources put inside along the zeta axis, with off axis, like some tube system for the external calibration, even like a small submarine to go in case of some, which I cannot imagine, like, but yeah, people are working on it. So, and plus we will have, build, so there is R&D ongoing and prototype is being built of the tau detector, so which is like Taishan Antineutrino Observatory. So 30 meters from the Taishan 1 core, so the nuclear power plant of Juno, we will construct like very small but very precise detector, cooled to minus 50 degrees with like very high energy resolution, like really like 1-2% energy resolution. And this will check these ideas of like different fine structure in the non-oscillated reactor spectrum. So these are the...
Is the main challenge the fact that, I mean, you can do that for smaller detectors like of the size of Borexino, but this guy is a 20
not really. This would be like 2 tons, even smaller.
Yeah. No, so the challenge would be to get that kind of resolution over the home. I mean, the detector should be homogeneous, or at least should be characterized to that level of accuracy to maintain that.
No, but I mean, there are exactly so we will measure with 1-2% precision very nearby the reactor with a small detector. We call it tau, to have a reference unoscillated spectrum of reactor.
Okay.
Then at 53 kilometers, we will have 20 kiloton Juno detector that for which we say, okay, we know the unoscillated spectrum and we want to measure the oscillated pattern, but there we need 3%, not 1% energy resolution. And this 3% we believe we can reach by keeping the high statistics of collected photons to have the good statistical error, plus all the possible systematic, especially the liquid scintillator has nonlinear energy scale. So this has to be very well calibrated.
So the photon response, I mean the photomultiplier response, as well as the liquid scintillator response have to be completely under control over a period of time, over a few years.
And you are very right. It's, I mean, we need like 6 years of data taking to get like 3 sigma for mass ordering. And so we have to keep not only stable, because I mean, even if it's slightly unstable, we will regularly calibrate. And but we need it really that the lifetime of the PMTs and everything is, because if we lose PMTs, as we for example lost in Borexino 50% almost at the end. If we lose PMTs, we will lose the resolution and we cannot measure the mass ordering. So it's really not only small changes. This we could calibrate, but we cannot lose the PMTs.
Incidentally, what is happening to the Borexino scintillator as well as the photomultipliers?
So to see
that was my question.
Scintillator, we did not. You mean like when we've been taking data? Like it was quite stable.
No. I think the data taking you have stopped. You said.
But
what is happening to that?
Empty.
I mean, is that being given to somebody or how?
No, I think it will be just. I mean, somehow. Like it will be not used, destroyed somehow. Yeah, we paying a lot of money.
No, so if somebody is interested in that, they would be willing to give it away, or
I am not even sure if it right now exists anymore, because I think there was no, also, you know, I mean, if you don't take precautions in the unloading, it gets radioactive. So if you expose it to air and everything, it's not pure anymore.
Okay.
So it is not like Icarus detector that you can, you know, ship to US basically.
No, yeah.
Yeah, this is exactly my question was that after dismantling, what you guys did with the Borexino detector, because, you know, I'm a big fan of Borexino. Like that detector showed us that how to go to lower energies. Like you reach below 1 MeV and you do a fascinating physics, right? You know, you see the cycles of solar neutrinos there. And I thought that maybe someday Borexino will show us a path how to detect the relic neutrinos, because they are even much lower energies. And I thought that
I think that that's the problem. At the Kev scale, you have the background in organic liquid scintillators. You have carbon-14, which has endpoint of 156 Kev. So, I mean, below that, you cannot really measure anything.
Right. I understood. But I was always hoping that, you know, it is showing us that we can reach up to that. Now you work hard, do something, you know. There are experiments which are, you know, talking about now seeing the relic neutrinos also, right? You know, So, but yes,
they involve tritium. Sanjeev, they involve tritium. You can't use a scintillator. There is a Q value to anything. So
right.
Yeah, with liquid scintillator, no chance.
Yeah, they use tritium. Yeah, it is also US-based
You
experiment.
have to have positive Q value, and you have to have a spectrometer, a very nice spectrometer.
Right. Just last, Livia, thanks for your detailed comments. So, what is the prospect of this ocean bottom detector? Like, I follow it closely because we work with Bill. So, Bill is one of the person, right, for ocean bottom detector. So what is the status?
I mean, I think originally it was John Laird and Steve Dye from Hawaii. I think there was some revival of the idea with Sirocco and Bill being involved, but I am not aware what exactly is the status. I mean,
because Bill recently visited Hawaii, John, and they had a meeting. So
I think there is some like underground infrastructure, underwater infrastructure in Hawaii, some cables that they would like to use, but I am not aware that there would be breakthrough in a way that somebody would like to pay for it. So I think there is the revival of some R&D activities, because you have to really prove all the underwater technology, the performance of the liquid scintillator at lower temperatures there, and so it's there is a lot of work to be done, and I think that some R&D is ongoing, but I don't think, but I might be wrong, that it's going to.
What was the depth at which it was being conceived?
So
under how much column of water?
I mean, several kilometers. I don't know exactly how is the depth around Hawaii, but it's not obvious. It should be on the floor.
But they have a money. But they have a money for R&D now. That is for sure. I know that, you know, they have money for R&D.
Yes, for R&D, yes. But then to build the detector, there is a long way from R&D. Yeah. But it's a success. I mean, because I think it was for many years it was really standby. So I think the R&D got renewed.
So they are saying that this detector will undergo operational deployment test at 1 kilometer depth seafloor in 2022, basically.
Oh, really?
Yes.
But how big detector?
That is a prototype. 20 kg
prototype. How much?
20 kg prototype liquid scintillator detector.
Okay, so it's really for nothing about geoneutrinos, just for the technology, right?
Yeah, just for the proof of the principle, basically.
Of placing the liquid scintillator. I mean, with 20 kilo, you cannot measure any geoneutrino. It's just really for the technology of the underwater and liquid scintillator, right? You can.
Yeah, but that is the first step, right? That is
absolutely.
Right.
I think it's a big success with respect to stopping all activities. So absolutely.
Yes. Maybe that is the future of geoneutrinos, right, Livia? Because
That's what
after
I said.
Borexino and KamLAND,
That would be the experiment, because I think the main question is the amount of uranium and thorium in the mantle. And on top of the ocean, the overall signal, it's like 80% from the mantle, because the oceanic crust has much less uranium and thorium than the continental crust, and it's much thinner, 8 to 10 kilometers with respect to 30 of average continental crust.
Right.
So that would be absolutely my favorite.
Right.
I think
I'm also closely following. So I will get in touch with you, Livia. Like you know that we have started this multi-messenger tomography of Earth activity, and we had a meeting with our organizational team, and we were thinking like whether geoneutrino community is interested to join hands with us. Like there should be a nice integration if they are at all interested, because geoneutrino is a big community. There are people working for both the experiments. There are experts. There are geochemists, and then neutrino physicists. So there was a discussion, and we will reach to you or maybe Bill just to get an idea like what geoneutrino community think. Like at some point you need to integrate all our efforts, so that we become visible as a community to probe Earth with weakly interacting neutrinos, and all the pieces have to be connected. But I just didn't get time over the last few weeks. But that was the recommendation. They were asked me, like Francis Halge and Patrick Huber. We had the organizational committee meeting, and we were thinking like next year I think it will be in AIPC Paris. Veronique will organize this workshop, and then I talked about your place at Mainz for the 2024 tomography workshop. Then the question comes like how should we move forward so that this become visible? One of them is the white paper that I will be in touch with you. But we need to discuss that whether geoneutrino communities are willing to join hands, because after now Borexino is over, KamLAND is also almost over, and then if we need to keep the activity and momentum going, we need to join hands basically. And
absolutely.
So we need feedback. Like we don't want to rope in somebody's territory basically. It has to be a smooth merging. But so we will come back to you. We will discuss, Livia, offline.
Happy. Yeah.
Right. But thanks a lot, Livia, for your patience and giving this colloquium for us. And such a long question-answer session, but I thoroughly enjoyed it.
I am impressed. Thank you very much. It feels nice.
Right. Thanks a lot, Livia. Please share your slides with us if you are comfortable.
Absolutely. Should I send it to you?
Yeah, send it to me, and we will put it on our social media handles. And as again, please keep helping our students. They need exposure for big experiments.
I have currently 2 Indian students.
Right. So maybe in future some of my students can also participate in some of the activities. Anyway, Amina is working with you. I'm very glad that she is working with you, with your students. Yeah, but I really want to thank that you are helping, and that's why the community grows. People can dream of being a part of big experiments and do good analysis, make contributions. So I really want to say thank you, and thank you for this colloquium. And in future, like my appetite is not fully covered because I just learned geoneutrinos. I told you that we want to also discuss the Juno, the reactor, the main hot topic. Yeah, maybe we'll catch you again sometime. Okay.
Why not also solar neutrinos? For instance, the CNO cycle neutrinos was quite a very interesting result that they had.
Very interesting. Yeah. If you remember, Professor Ranucci gave a colloquium. We organized that ourselves. Professor Giovanni Ranucci. So he gave a night after the CNO discovery. Livia, we organized a colloquium by Ranucci because I worked with Milan people in 2018 for NSI analysis.
The non-standard interactions. Yeah.
Right. So I know those people very well. So Ranucci gave a nice colloquium, and we were excited. like I kind of feel little bit, upset that Borexino is no more.
Don't tell me, Sanjeev. I hope we are not broadcasting this.
Right. But you see, I also understood the risk of running it. Basically, there was some risk involved in the Gran Sasso lab, right? Something
Not
like
really.
that.
I think that once you are hermetically closed, and any air leak or something would be disaster for our detector. It's much more safer to run and not to touch anything than to unload 300 tons of even more dangerous liquid.
Right, and dump it somewhere.
Every truck, it's a danger, filling, unfilling. Yeah. If you keep it, even the big earthquake, if you are underground having a hole, all the waste it's somehow spread around the underground, so nothing happened. But unloading trucks so many tons of dangerous. I mean, the liquid is dangerous. But unloading it is much more dangerous than filling and letting it there forever.
Right. Yes. But I saw the detector. I touched it because there was like, aluminum foil, a kind of cover outside, right?
It's the thermal stabilization.
And there was a stair to go up, basically.
Oh,
Yes. So I went there and I saw that, Professor Bellini took us when there was a Gran Sasso, there was a meeting, right? At LNGS basically. So there was a trip to
geoscience, right?
Yes. Anyway, Livia, it was really nice, and let's keep in touch. And
absolutely,
we are excited to hear more from you, and we will also tell you what we are doing for multi-messenger tomography with oscillations.
Thank you, and thank you everybody for invitation and also for really lively discussion. I mean, it was really exceptional. Thank you very much.
No, we are really grateful to you. You stayed so long and then discussed patiently. Maybe all the questions are not relevant, but you answered.
I mean, it's nice to see the reaction. I mean, it's really I really enjoyed also. So thank you very much.
Thank you, Livia. Thank you.
Thank you.
Yeah.
Bye. I'm looking forward to your seminar next week.
Okay. Yeah. I need to work on that. Bye.
Thanks. Bye.